Hey everyone, so we are now covering 1.5 polynomial functions and complex zeros. So the zeros of polynomial functions, given a polynomial function p of x, if p of a is equal to 0, then a is a 0 or root of p of x. If a is a real number, then if x equals a is a 0 of p, then x minus a is a linear factor of p. So all of this is just saying that, when you have your graph, any point that crosses or touches the x-axis is considered a 0, right? Or in this example, as they call a, right? And then they're saying, well, if the a is a factor, then you can say that x minus a is a linear factor, right? This is something we should be very familiar with, right? When we factor out a polynomial, you always end up, x minus 3, x plus 2, right? These are the factors that it's talking about. And then I would have x equals 3 and x equals negative 2. Those are my x equals a situations, right? So now, what if I have repeated zeros? Well, that comes into play with something called multiplicity. So if a linear factor is repeated n times, the corresponding zero of the polynomial has a multiplicity n. So if I had an example, let's say I have x plus 3, x plus 3, and then an x minus 2. I can rewrite these as x plus 3 squared, right? Because I have 2 of them. So this means I have a multiplicity of 2. That's all it does, is it basically just tells me how many times that factor occurs as a 0. But that means that there are special rules. So we have our rules of multiplicity. So if the factor has an even multiplicity, the graph bounces. So if you're looking at this graph that we have over here, we can see that there is a 0. So this is actually the function. F of x is equal to negative 0.01 x plus 4 x plus 1 cubed and x minus 3 squared. So this x minus 3, remember that's really that x equals a positive 3, has an even multiplicity. It's 2. So what happens is, when I get to that point on the graph, my graph does not actually cross the x-axis, it bounces off of it. While the odd one, so this is the second rule, odd multiplicity, the graphs will cross. So I have here x equals negative 1 has a multiplicity of 3. So at negative 1, my graph crosses the x-axis. And it's the same thing over here. This x plus 4 is equal to x equals negative 4. And it has a multiplicity of 1. Well, 1 is an odd number, so my graph would cross over at negative 4. So you can go ahead and complete these examples. We will go over them in class together. So all you have to do is determine the degree, find all real zeros, and state the multiplicity of each 0. Moving on, we have complex roots. Well, complex roots are roots of a polynomial with an imaginary number. They will not appear on the graph, obviously, because they are imaginary. Complex roots are written as a plus bi and are conjugate pairs. So that's a few things in that definition that I want to go over. So here I have an example of a function with complex roots, right? Here I have x squared minus 1. Well, if I set this equal to 0, x squared plus 1 equals 0, I subtract 1 to both sides, and I get x squared is equal to negative 1. Well, this is when I would do my radical, and I get that x is equal to plus or minus the square root of negative 1. Well, that's not going to work, so remember that this is really x is equal to plus or minus I, right? So there's my imaginary component. Now remember that when we wrote about this in our notes, which we should have covered in Algebra 2, a plus bi, a is my real component, bi altogether is my imaginary component. right? And they're always conjugate pairs. So in this example, I have plus or minus I always have to have a plus or minus. So we're going to go through these conjugate examples really fast because they're simple enough. So you should pause the video and write the conjugates on your own before watching me do it. So the first one here is 4i. Well, its conjugate would be negative 4i. If I have just I, it would be negative I. Now here I have that a plus bi set up. Well, 2 is going to stay the same, but now this negative is going to become positive 3i. And now in D, so D I like because 4 here has a negative. 4 does not change. The real portion of a complex root will not change when you write the conjugate. It will always stay as negative 4. But the second sign will change. So you would have negative 4 minus 2i. And now we have the fundamental theorem of algebra, which says a polynomial of degree n has exactly n complex zeros when counting multiplicities. So, best way that we can go through this is just going through this example right here. So try to pause it, try to do it on your own, and then you can see how we do it together. So the graph of the polynomial function f of x is shown in the figure above. It is shown that x equals I to the square root of 3. I square root of 3 is a 0 of f. If f has degree n, what is the least possible value of n? So first I want to look at my graph, right? I'm going to identify all my real zeros. So I'm going to write over here real zeros. Well, I have one at negative 1, and I have another one at 3, right? Now, if I were to write these out as factors, I can say them as x plus 1. Now, according to my graph, at negative 1, my function bounces. So it's going to have a multiplicity of at least 2, right? Remember, we're looking for the least possible value of n. Could it be a multiplicity of 4? Sure, but at least it has to be 2 so that it bounces off the graph. Then, at 3, so x minus 3, I cross, meaning that the least number multiplicity I can have for that one is a 1, right? And now, I'm looking at this I square root of 3. Well, so let's say imaginary zeros. I have I square root of 3. But remember, I always have a conjugate. So I would have negative I square root of 3, meaning that I need to have at least, let's see, 1, 2, 3, 4, 5. So my function needs to be at least 5. So n needs to be greater than or equal to 5 so that I can have this many zeros, okay? Now we're going to solve nonlinear inequalities. Well, here we have a bunch of steps ready to go. So let's go ahead and do this example. So the first part says set f of x equal to 0 and solve. Now, if you have this in an unfactored version, you would have to factor it out. But it's already factored for me, so I can just say x minus 3 equals 0, x plus 1 equals 0, and x plus 4 equals 0, which gives me x is equal to 3, to negative 1, and to negative 4. The next thing I'm going to do is I'm going to create a sign chart. So basically what's going to happen is I'm going to draw a line, essentially a number line, and then I'm going to put, here's my negative 4, here's negative 1, and here's 3. This line does not have to be accurate, right? You're just putting the points that we just found in step 1, right? Then I'm going to test values to see if they're positive or negative. So I'm going to test the values that are one on the left side of negative 4, in between negative 4 and negative 1, in between negative 1 and 3, and then greater than 3. So I'm going to go ahead and I'm going to pick 4, 0, -2, and -5. I don't want to complicate my life. I try to pick the simplest numbers that I can. Now, I plug these all back into the equation. So I would have -5 minus 3, -5 plus 1, and -5 plus 4. Then I would have -2 minus 3, -2 plus 1, and -2 plus 4. And then 0 minus 3, 0 plus 1, 0 plus 4. And then 4 minus 3, 4 plus 1, and 4 plus 4. So this first one would be -8, -4, and then a -1, which would be -32, which would be a negative sign on this portion. So basically from -infinity to -4, my graph is negative. Now I'm going to look for the next one. So here I have, that's -5. That's going to be -1. And this is going to be a positive. So really, I don't have to actually solve what these values are. I can just say that the final answer is going to be positive or negative, which in this case it would be positive because I have 2 negatives. So 2 negatives give me a positive. So between -4 and -1, my graph is on the positive. Then I'm doing the next one, which is -3, +1, +4. Well, there's only one negative, which means that between -1 and 3, my values are going to be negative. And in the last one, I have 1, 5, 8. All 3 are positive, so this one is positive. Now, the last part is to interpret the sign chart. So essentially, what I'm going to say is that I'm going to write it as an inequality. Okay, so I'm going to say actually, you should write your answer in interval notation. And remember to think about the endpoints. So my endpoints were -4, -1, and 3. So from -4 to -1, and then 3 to infinity. Now you might be wondering why I only included these 2 intervals. And the reason is because I have to look back at my original function, right? I'm looking for values greater than 0. Well, that means that I'm only looking for the positives, right? And my positive range areas were between -4 and 1 and 3 to positive infinity. So if you wanted to write it in as an inequality, because technically we're solving inequalities, you would say -4 is less than x, which is less than -1. And you would say x needs to be greater than 3. Okay, so then you have this example here to try out on your own. So again, pause the video. We will do this one in class as well. And then we're going to move on to the next one, determining the degree of a polynomial given a table of values. So our one and only step is to use successive differences. So we should remember successive differences from last year in our Algebra 2 class. Basically, what you're going to do is find the difference between your y values. So the difference between -2 and -3, well, that's -1. From -3 to -1, -2. From -1 to 4 is 5. And then from 4 to 12 is 8. If they are all the same, then that is your degree. But in this case, they are not the same, so I have to keep going. So the difference between -1 to +2, I'm sorry about that, +2, is going to be 3. From 2 to 5 is 3. And then from 5 to 8 is also 3. So because I only had to do this twice, my degree is 2. Meaning it is a quadratic. So it's a 2 because the second difference is constant. Okay, and the last thing to go over are even and odd functions. So you have here, even functions are symmetric over the y-axis, and the key to doing that algebraically is you need to replace x with a negative, right? So here you have your example. It's like very, very small. I'm sorry about that. But if I were to replace every single x with a negative x, right? So x to the 4th, well, that would still be a positive x to the 4th. X squared, negative x squared is a positive, so that's still 8x squared plus 1. If I can replace every x with a negative x and get the same answer, then they are even functions. They are symmetric over the y. When you are looking at them, your y-axis should act as your mirror, and that's what you would be looking at. Now, when it comes to odd functions, they are symmetric about the origin. So not exactly the mirror, right? They're going to kind of flip over. And in this example, when you replace your x's with negative, you should get basically the opposite of what's there, right? So I'm going to have negative x cubed minus 9 negative x, right? Now x cubed, negative x cubed is going to be a negative x cubed, and then negatives become positive 9x. So this is an odd function because it is the exact opposite in every possible way. Okay, and then now you have 4 examples that I want you guys to work on. We will go over those in class as well. So make sure that you are studying and reviewing the notes.